Hello, welcome to the Algebra 1 Enrichment chapter titled Radical Expressions, the Quadratic Formula, and Absolute Value. We are going to start this chapter by talking about simplifying radical expressions, what it is, what you need it for, and how to simplify it. So if you turn your note packet to the first page, at the top it says Simplifying Radical Expressions. And your objective is, it says students will simplify radical expressions. Before we start this and before I give you an introduction, we need to look back and recall perfect squares. And we're actually going to list the first 20, not the first 15. You need to remember what a perfect square is in order to simplify a radical. So we did this back in September with chapter 9, so I'm hoping you remember these. Okay, so the first perfect square is the square root of 1, which is 1. Anytime you take the square root of something and you get a nice number, that's a perfect square. Second one, square root of 4, which is 2. Third one, square root of 9, which is 3. Next one, square root of 16, which is 4. Next one, square root of 25, which is 5. Sixth one, square root of 36, which is 6. Next one, square root of 49, which is 7. Square root of 64, which is 8. Square root of 81, which is 9. Square root of 100, which is 10. So let me pause for a second to make sure that you're with me. Again, remember, when you take the square root of something and get a nice number, that's a perfect square. Okay, let's do 11 through 20. Square root of 121 is 11. Square root of 144 is 12. Square root of 169 is 13. Square root of 196 is 14. Square root of 225 is 15. Square root of 256 is 16. Square root of 289 is 17. Square root of 324 is 18. Square root of 361 is 19. And square root of 400 is 20. So here's the first 20 perfect squares. Make sure if you don't remember all these from chapter 9, that you try to look over these and remember these. Very helpful when you're simplifying radical expressions, which I'm going to explain here in a minute. Also remember, there are more perfect squares. These are just the first 20. Okay, so let's get right into our examples. So our examples here, we're getting right into simplifying radicals. This first set of examples uses the product property of radicals, which says we can split up these radicals into two different radicals being multiplied together as long as the product is equal to the number that we're given. What I mean by that is, look at letter A. We have the square root of 32. We need to simplify this, but not change it to a decimal. We want to simplify it completely, but not use your calculator and change it to a decimal. First question that you want to ask yourself is, what is the largest perfect square that goes into 32? So you could go through and start with 1. We know 1 is a perfect square. Yes, it goes into 32. Let's go to the next perfect square, which is 4. 4 goes into 32. There might be a larger perfect square that goes into 32 to make it easier for us. So go to 9. 9 is a perfect square. The square root of 9 does not go into 32. So let's try a couple more. Let's go to 16. Okay, 16 is a perfect square, and it does go into 32. 16 is the largest perfect square that goes into 32. So we're going to change the square root of 32 to be the square root of 16 times the square root of 2. This is using the product property of radicals, which says you're allowed to take a square root and split it into two square roots or radical symbols, but if you split them up, one of them has to be a perfect square. We chose the square root of 16 because it's the largest perfect square. If you use 4 divides into 32. You can still use that, but it's not the largest perfect square. So at this point, I always say, find the largest perfect square, circle whatever your perfect square is, and we need to take the square root of it. The square root of 16 is 4. So you're going to write down that the square root of 16 is 4. Drop down the square root of 2. That's your final answer. That is simplified completely, but we did not change the value of square root of 32. They're equal, they're the exact same. You just have to simplify it completely. We are going to use these throughout this enrichment packet for quadratic formula. You'll use this in geometry for a lot of concepts. So there's a lot of application to simplifying radicals. Now let me show you the same problem, but let's say you don't like or you don't understand why use the largest perfect square. So let's say you started it and you changed 32 to be square root of 4 times square root of 8. Because we know 4 divides into 32 8 times, and we know 4 is a perfect square. So you can still change it to be any perfect square. I just want to show you that it's easier using the largest perfect square. Square root of 4 is 2. So take the square root of 4, write it down, rewrite the square root of 8. Next step, this square root of 8, you're not done. It's not completely simplified. You can change square root of 8 to be square root of 4 times square root of 2 using the product property of radicals. Once you do that, you realize square root of 4 is a perfect square. So here's where it gets tricky. Circle the perfect square, and then underneath that, rewrite the 2. Square root of 4 is 2. So we have 2 times 2. Drop down the square root of 2. 2 times 2 is 4. So you get 4 square root of 2, which is the same answer we got with using the largest perfect square. In my mind, it's easier to use the largest one, but again, you don't have to. Okay, let's go to another example. Letter B, square root of 24. So you ask yourself, what's the largest perfect square that goes into 24? So of course 1 goes into it. Let's go to 4. 4 is a perfect square, it goes into it. Let's make sure there's not a bigger one. 9 is a perfect square, but it does not go into 24. 16 is a perfect square, and I'm just going through this list. 16 is a perfect square, but it does not go into 24. So we know that 4 is the largest perfect square that divides evenly into 24. So using the product property of radicals, we're going to change it to square root of 4 times square root of 6. Circle the perfect square, take the square root of it. Square root of 4 is 2. Take the square root, get rid of the square root symbol, rewrite square root of 6. Ask yourself, are there any perfect squares that go into 6? There's not, it's just 2 times 3. So that is your answer, completely simplified, and again, it is equivalent or equal to the square root of 24. Okay, let's try an example with variables. This is when it gets to be a little bit harder. So if we have the square root of 25x squared, different, again, like I said, because we have these variables. The first thing I want you to do if you have a variable is using the product property of radicals, separate them into 2 square root or radical symbols so that it's easier for you to simplify this completely. Now looking at it, you want to ask yourself, are any of these already perfect squares? Well, 25 is a perfect square, so I'm going to circle that. And the square root of 25 is 5. So I'm going to write that down because 5 times 5 is 25. Now variables, this is something we haven't talked about yet. If a variable has an even number exponent, it's already a perfect square. So any variable with an even number exponent, I'm going to circle this, is a perfect square. To take the square root of it, all you do is divide the exponent by 2. 2 divided by 2 is 1. So x to the first power is the square root of x squared. The reason is x times x is x squared. You can also just write it as 5x. So the square root of 25x squared is 5x. And if you check your answer, 5x times 5x is 25x squared. So again, any even numbered exponent, to take the square root of it, divide it by 2. Okay, let's go to letter D. Letter D, we have square root of 49y cubed. First thing I want you to do when you have a variable is use the product property of radicals and split them up. Then look at any of the numbers, see if any of them are already perfect squares. 49 is already a perfect square. Square root of 49 is 7. Now looking at that y cubed, it's an odd number. So the way it's written right now, you cannot take the square root of it because it's not perfect. So I want you to split up y cubed. So I want you to think, well, can I change y cubed to something to be y to the something power times y to the something power, one of them being an even numbered exponent? You can. You can make one of them y to the squared and one of them y to the first. When you multiply same base, you add exponents. We're not changing the value of this. Y to the second times y to the first is still y to the third. So in other words, I always just ask myself what the largest even number is that we can change the exponent to, and I use that as one of the variables. Circle what's perfect. Square root of y squared is the perfect square. When you have an even number exponent, take the square root, divide the exponent by 2, so that's going to be y to the first, because 2 divided by 2 is 1. Rewrite square root of y, so your final answer is 7y, square root of y, and again, that is completely simplified. Okay, let's go to letter E. Oh, sorry. Wrong letter E. Okay, let's go to letter E. Letter E, the problem we have here is 3 and then square root of 50 x cubed y squared. Now, letter E in your packet is a little bit different because there's a number in front. Anytime there's a number in front, that number is just going to stay there. When you end up taking the square root of something, you will multiply it by 3. So we want to rewrite the 3, split up the number and 2 variables using the product property of radicals. After you do that, see if any of them are perfect squares. Right now, the only one that's a perfect square is y squared because it has an even number exponent. The square root of y squared is y, so take the square root of it, move it in front. Now we're gonna change 50 to be something times something is 50, one of them being a perfect square. So I want you to go through your list of perfect squares, figure out the largest perfect square that goes into 50. Okay, hopefully you found out or knew that 25 was the largest perfect square that went into 50. So we changed that to be 25 times 2. Next, square root of x cubed. Find the largest exponent that's even that goes into 3, or I should say that we can rewrite it so that something plus something is 3. X squared times x to the first is x to the third, because you just want to add the exponents and still get 3. Circle what's perfect. Square root of 25 and square root of x squared are both perfect. Once you find the perfect squares, remember you move them out back in front, and they are going to need to be multiplied by the 3y. So square root of 25 is 5. Okay, so I'm going to put 5 times 3. We'll multiply that in a little bit. Rewrite the y. Rewrite the square root of 2 because that's not perfect. Square root of this x squared is x because 2 divided by 2 is 1. This x to the first is not perfect, so write that inside the square root. Okay, next step, all we need to do is multiply this 5 times 3. We get 15. And I'm going to change the order of these x's and y's so that they're in alphabetical order. You really don't have to do that, but to me it makes it easier. And then your square root of 2x were the only two terms that are not perfect. We leave that inside the radical. That is the completely simplified answer. Again, it's the exact same thing as the original problem. We just simplified it. Okay, if you have questions on this, let me know when you come see me for your homework. If not, I want you guys to try letter F and G. Okay, so try letter F and G, and I will check that whenever you come to see me. So again, try F and G. Pause the video while you're trying it because I am going to go to letter H. So pause the video, try F and G. Okay, now that you've tried F and G, I will check that answer when you come to see me. Let's do letter H together. Okay, letter H. This one's a little bit different just because you have a negative in front. That negative in front, you just leave it there until you get to the very end of the problem. It just makes your entire problem negative. So first step, split up everything inside the radical symbol. Okay, so we have square root of 20, square root of m to the 10th, square root of n to the 2nd. Ask yourselves, are there any perfect squares as of now before we split anything up? Yes, here's an even numbered exponent. Here's an even numbered exponent. So I'm going to circle those. We can take the square root of them, which means just divide the exponents by 2. So 10 divided by 2 is 5, so we have m to the 5th. 2 divided by 2 is 1, so n to the 1st. Square root of 20 now we can change to be something times something. One of them is a perfect square. So hopefully you thought we need to change it to be 4 times 5. 4 is the largest perfect square that goes into 20. Circle 4 because 4 is a perfect square. Square root of 4 is 2, so take the square root, move it back out in front. So negative 2m to the 5th, n to the 1st, square root of 5 is our final answer. That square root of 5 cannot be simplified any further. Okay, so that's the first part, using the product property of radicals. I would like to do one more section in this first lesson with you in this recording. I'll save the last section for the second recording. Okay, so we're going to go to number 2 on that second page of your notes. Okay, the directions in number 2 say simplify using the quotient property of radicals. So these are pretty easy. The quotient property of radicals says taking a fraction that's already inside a square root symbol. First thing you need to do is split them up. So in other words, instead of square root of 13 over 100, change it to be square root of 13 over square root of 100. After you split them up, you want to simplify and see if any of them are perfect squares. The only thing that you don't want is you do not want to have a radical in the denominator of your answer, ever. So the square root of 13 is prime, so that cannot be simplified any further. There's not a perfect square that goes into it. Square root of 100 is perfect. Square root of 100 is 10. Take the square root of it, and that's your answer. That's all you need to do using the quotient property of radicals. Okay, let's look at letter B. Letter B, we have a variable. So using the quotient property of radicals, first thing you want to do is split them up to be square root of 1 over square root of y squared. Square root of 1 is a perfect square, so I'm going to circle it. Square root of y squared is a perfect square. Square root of 1 is 1. The square root of y squared is y, because 2 divided by 2 is 1. So that one's really easy. If you want to check your answer, we know that 1 over y times 1 over y is 1 over y squared. Okay, I want you to try C and D. Pause the video, try C and D. I will check your answers when you come to see me. So try C and D on your own. Pause the video. Okay, hopefully you tried C and D. Again, I will check those when you come to see me. We're going to do E and F together. Okay, letter E. We have square root of x squared over 400. So letter E, first thing we want to do is using the quotient property of radicals, split them up. So we have square root of x squared over square root of 400. Once you split them up, ask yourself, okay, well, are any of these perfect squares? They're both perfect squares. Square root of x squared is x, and square root of 400 is 20. So the simplified answer for letter E is x over 20. That one's pretty easy. Okay, let's do one more together. Letter F. Square root of 324 x squared over 25. Okay, first thing we want to do is split them up. So we're going to split them up to be square root of 324 square root of x squared over square root of 25. So using the quotient property of radicals, and actually in the numerator, also the product property of radicals, split them up. So let's look at the perfect squares. Square root of 324 is a perfect square. Square root of x squared is a perfect square. And square root of 25 is a perfect square. So this one also works out really nicely because we can just take the square root of each of them. Square root of 324 is 18. Square root of x squared is x. And square root of 25 is 5. That's our answer, completely simplified. Okay, so that ends the first lesson of the Algebra 1 enrichment packet that you guys had in front of you. We will talk about rationalizing the denominator in video 2. So please, before you do video 2, come see me so I can look over your notes, answer any questions, and also give you the assignment that goes with this lesson. When you finish the assignment, come see me. I will have an answer key for you to check to make sure you know what you're doing. Please do not fall behind and do not wait until right before the test to tell me that you have no clue what you're doing, okay? Because this stuff all builds on each other.